Here we're going to look at capacitors connected in series. Now, whether it's a capacitor or any circuit element that's connected in series, the characteristic of a series connection is that each element, in this case each capacitor, that is connected will see the same flow of charge through it. So there's no branches, there's nowhere for the charge to break out from, so that the flow of charge through each of the devices remains the same. Now, for us, in analyzing capacitors, we are going to get a lot of mileage out of same color, same voltage, so we'll get back to the flow of charge in a moment, but let's start by getting our same color, same voltage. Metal touching the top plate. Now, when we go through the gap, we lose the metal touching metal, so here we have to go to a different color, different voltage. We'll talk about that voltage in a moment. Go across the gap, different color, different voltage. So we'll get to that. And then finally, our last voltage that's connected to the bottom plate of the battery will always be at 0 volts. So we know, let me change that from light blue. Let's go to purple. So we'll make that our purple. So we know that the light blue here is 0 volts. We know that the red is 3.5 volts. Now we don't know the purple or the green yet. Now the flow of charge has to remain the same. So maybe the most important thing you remember about the concept of the series capacitors is this little bit that I'm going to now explode down here, that all the Q's have to remain the same. And why is it that all the Q's remain the same? Well, it's a domino effect. So when the battery pushes that first charge here, that first charge is going to push a positive charge down to the other end of the purple, onto the top plate of our second capacitor, and we're going to get a net negative here. And then that positive, again, domino effect, pushes a positive here. We're left with the net negative on the bottom. So we get the same Q because the flow of charge, series connection, has to be the same through each of the devices. Now, what does that mean in terms of our voltages? So now we know that the Q's are all the same, and the 2 coulombs I have here is not a calculation. That's just by example, right? So the 2 coulomb here, let's not use green because we're using green elsewhere. So the 2 coulomb here is just by example. So if all the Q's are 2 coulombs, what would be the voltage drop across the first capacitor? Remember, V equals Q on C. That's not the voltage on the top or the bottom plate necessarily. That's the voltage drop. So what we get is a 2 coulomb charge on the top plate. We get the 1 farad capacitor. We get a 2 volt voltage drop across the first capacitor, which means that for our purple, we get 3.5 minus 2, we get 1.5 volts in there for that purple. Now, when we do the same for the green, we see that on the second capacitor, we still get a charge of 2, right? Same charge on each, domino effect. Capacitance is now 2. We get a 1 volt voltage drop across the second, so we go from 1.5 to 0.5, and we don't have to calculate the last voltage drop. We go from 0.5 to 0, but if we do calculate it, look at what we get. On that last capacitor, we have our still same 2 coulomb charge. We have a 4 farad capacitor, so everything is consistent, as of course it must be in physics. So conceptually, everything we've talked about, by far the most important thing that you need to know, because the rest is the mathematics that kind of falls into place. Since voltage is an energy concept, conservation of energy dictates that the voltage of the battery has to equal the voltage drops, right, across the capacitors, and the equivalent circuit, where if we were going to replace all 3 of those capacitors with 1, would now have the same charge on our equivalent capacitors. All the Q's are the same. And so when it says all the Q's are the same, that means all the Q's, even the equivalent. So the equivalent capacitance, the Q1, the Q2, the Q3 are all the same. So they end up canceling each other out, and we see that we have our equivalent capacitance. 1 on C123 is 1 on C1 plus 1 on C2 plus 1 on C3. Now we have to be a little careful with our mathematics, of course, because what we have calculated when we do the calculation, the 1 plus the 1/2 plus the 1/4, the 1.75 farads, that is not the equivalent capacitance. That is 1 on the equivalent capacitance. So we actually have to invert it at the end. So series connections have a little bit more steps, a little bit more to think about. But the equivalent capacitance is 1 on 1.75, so that we see, if we did just look at our equivalent circuit and looked at Q equals CV, our equivalent capacitance, 0.571, times the voltage, 3.5 volts, gives us a Q of 2, which was what we started with, right? Q of 2. So everything is definitely consistent. So equivalent capacitance, when they're in series, is reciprocal, but everything is reciprocal. So please do not forget to take the reciprocal of your final calculation, as we did here, to get the actual equivalent capacitance that we would be using. So we will be looking now at combinations of circuits after this that have both series and capacitors together.